Whoa, cool. All right, so let's directly get into it. So the main player today is a so-called Loyenga pair. Loyenga pair consists of two things. First, the Y, that's a smooth rational projective complex surface, and D, an anti-canonical singular nodal curve. Okay, and this curve consists of L irreducible components, and these components I always label from D1 to DL. And there is a comment. You don't see the pointer. That's very sad. Okay, how do we do it then? I have a mouse. Yes. Okay. All right, cool. There is one little extra condition we also assume throughout this talk, namely that all these components are Neff. And in this case, we call this Loyenga pair Neff. All right, so maybe I should present an example. So as our surface, we take P2 together with the choice of a line and a smooth conic intersecting the line in 2 points. And let us check that this is indeed anti-canonical. So the line is hyperplane class, the smooth conic 2 times the hyperplane class. So these two perfectly match up and give minus the canonical class. Perfect. Okay, and if we have such a Loyenga pair, we want to associate 3 geometries to that. With these 3 different geometries, to these 3 different geometries, then we will associate enumerative invariants. But yeah, that comes later. So for now, what are the 3 objects we associate to this input data? Okay, the first object is basically contains exactly the same information as before. We just equip the surface with the divisorial log structure coming from this divisor here, and then we obtain a log Calabi-Yau twofold. Calabi-Yau because the divisor is anti-canonical. Okay, so not too much happened. Yeah, this is a little different for the second geometry we associate to this choice, namely a local Calabi-Yau, which we obtain by we look at the class here. Then we take minus, or we invert and then take the line bundle. Same here. We invert, take the line bundle. Take the direct sum of these, we get a vector bundle. We look at the total space. So over each point in the base P2, we have a 2-dimensional fiber. So in total, we get a 4-dimensional variety, non-compact, and therefore we write this little word log. All right, and the third guy, this is so to say the intermediate step. So to go from here to here, we took the total space over both line bundles. Now we only take the line bundle over, by convention, always the last in the cycle, this here. So minus 2 of, and you see here, we don't have the P2 anymore. We decompactified. We deleted the locus of the divisor we had here, the line we had before, and we replace it by a Lagrangian. If you feel uncomfortable with that, think of this Lagrangian just as a substitute for the information of this divisor. In the story that follows, they will basically behave the same. But for the constructions we do, it's just convenient to have these geometric setups. All right, so this is how the construction would be. Yes? A little louder, please. Sorry. Yes. Yes, I should. sorry, so I take this and then I restrict to the C2. So I delete all the fibers over the P1, so over this line here. Yeah, that's an interesting question, and yeah, the thing is, so later, maybe can I get back to your question in the next slide when it define or explain you the enumerative invariants? Probably there's a better place to tell you what's happening. Okay, so before we proceed, I should tell you what the three geometries are in the general case. So if we have an L component pair, then here in the middle, we take the direct sum of all line bundles coming from these divisors. So in this case, every fiber over a point is L-dimensional. Add the 2 dimensions of the base, you get an L+1 fold. And here, as I said, by convention, we only take the line bundle over the last divisor. We take this total space here, delete the locus which is associated to these to the remaining divisors, and we replace the divisor by Lagrangian. Remark on that later. Okay, and in these geometries we want to perform certain curve counts. So I will use these numbers n here, labeled by the respective geometry we are counting curves in. And just to say, okay, I want the number of curves in a variety that's not a very well-defined question. We should fix some more constraints in order to indeed obtain a finite number. So the first thing we fix is the class of the curves in the geometry we're looking at. Then, for the time being, let's restrict our analysis to genus G curves. And I should be a little bit more accurate. We're not counting embedded curves, but we're looking at parameterized curves, aka stable maps. Okay, and now depending on which geometry we're in, we will also impose some more extra conditions. So here for the log Calabi-Yau twofold, we have this information of the divisors, and now the curves we want to count are those which meet each component in exactly one point, and in this point they must have maximum tangency. So if we have a curve of class D, the maximum tangency with an irreducible component di must be the intersection product. So that's the maximum we can obtain. And now I need a pen. Okay, so let's look at our example where we had y equal to P2, and let's have D equal hyperplane. Okay, so we compute D times D1, which is hyperplane class, is 1. D times D2 is 2. So the enumerative question we're looking at is how many tangents, how many lines are there which are tangent to D2 and intersect D1 in a point. The thing is, every tangent has this property because every line in P2 intersects. So we get a D2 whole of curves, so not a finite number. So, but yeah, we would like to have a finite number, and therefore what we do is we impose sufficiently many point conditions. So we asked, for instance, the line to go through this point here. So, and then you see, well, that geometrically makes sense. There's just a finite number. Okay, so in order to get a finite number, we impose enough point conditions. This always depends on the respective geometry we're in. But yeah, I didn't want to go into the details here too much. It's more or less, so you have your moduli space, you have the expected dimension, and then you cut down by imposing more and more point conditions until you get to degree 0. That's the technical idea. Okay, so I talked a lot about how we get this number here. So, and I didn't want to, write the geometry here. So y of d. I just put a log here. Same for the others. Simplify notation a little bit. Luckily, now for the local Calabi-Yau L plus twofold, it's a little easier. There we don't impose any extra conditions. We're just counting the curves there. All right, and for the local Calabi-Yau threefold, where we have these Lagrangians, there we also impose a contact condition. So, and I said before that you should think of these Lagrangians just as a substitute of these divisors. And basically the conditions we impose are more or less the same. So here we impose tangency. Here we are looking at stable maps which have a fixed number of boundaries, namely L minus 1. And each of these boundaries, one boundary always maps to one of the Lagrangians in the target. And then, so here I made the modest approach. So here I drew something in complex dimension and here in real dimension. So the complex one-dimensional curve, the real two-dimensional, has a one-dimensional boundary. And the contact condition with the Lagrangian is that we impose that we have d times di windings of this S1 around the Lagrangian. Okay, so basically, this is why I said earlier that they more or less behave the same. And now getting back to the question how we actually define these Lagrangians. The honest answer is we don't I don't really geometrically work in this setup and really make a curve count in this sense. So I'm not looking at the moduli space of stable maps with boundaries, because this moduli space is extremely ill-behaved. What we used was the formal approach of Li, Liu, Liu, Zhu, where they basically just remembered input data, or I should better say, do you know the work? Li, Liu, Liu, Zhu? The approach. So they use the idea that basically relative invariance should be a limit. So if you shrink this here together, the S1 of the Lagrangian, you shrink it together, that should give you a divisor that these pictures should be somewhat exchangeable. And they defined the invariance here basically through relative invariance. So they again compactified this geometry in a formal way and ended up with invariants which behaved as you would expect such naive invariants to behave if they would be well defined? Okay, so the answer is, okay, it was a very long answer. The answer is, I don't rigorously define the geometry. I just have something or a combinatorial setting which behaves like I would expect it to behave. That's satisfying? Yeah, sure. Yes. Yeah.
So again, you have a first operation compound. And what Yannik was saying about this word is that calculate the structure, either close the sample or some relative. So you have correct, yeah. That's not possible. Yeah, you don't have to see some events that things in the final. But the problem of the T times R migration that's we can see that possible. And in the final comparison.
Yeah. Okay, Andrea took over. Now let me take back the control. And now what log local open is all about is that these three a priori very different numbers, they're equal almost on the nose. So these are equal on the nose, while for that one here, one just has to multiply with a combinatorial factor, but not too complicated. And if you ever try to compute these numbers, it looks like such a relation is actually a miracle. Right, and this was uncovered by Busseau, Brini, Bangarel. So one you already heard speaking here, the other one left the room earlier because he knows the stuff too well. And now one could ask, can we push this also to higher genus? And there I'm lazy. I just form the generating functions for all these invariants here with form a variable h bar. And yeah, calculate all these numbers at once. And yeah, at this time, there's nothing here in the middle, just for the reason that the moduli space will have a negative expected dimension. So all the enumerative invariants you would have here, or most of them would be 0 in higher genus. So nothing to compare again. But also here again, these two are very different generating functions. Again, agree up to a factor here. And this is the factor we saw earlier, which is the difference that the Lth factor is factored out. And just the d times di got replaced by this sign here. Okay, so again, a very surprising explicit relation. Yes, there was a comment? No? It was just feedback. Okay. And I think my minute is gone. So I will simply, what? Yeah, okay. So, okay, maybe I do a very quick remark. So this side here, why it's exciting to have such a correspondence is, this side here is on the computational front very strong. There are, with the topological vertex, you have a very strong tool to compute these numbers here. Where on this side, these invariants usually have an interpretation in terms of Gauss-Seibert mirror symmetry. So they have a deep, they developed in a very geometric picture, and therefore the ways how to compute these numbers are very different. But this correspondence, somewhat marries these two different words. And yeah, I don't know. Maybe someone has seen this before. There is a toric diagram. Here's the scattering diagram. And while on the one side, if you have never seen this before, you're probably thinking, why is he showing me these pictures? But see, the complexity of these intersection numbers, of these numbers, they grow with the complexity of these pictures, so to say. Okay. So far, not much happened. Okay. Maybe I should explain. I was rushing a lot. So we were starting from our main example here, P2 with the line and the conic, and now we started to blow up and take always proper transform. So here we blew up 2 points on the conic, and so far not much difference. Now let's blow up a point on the line, and then suddenly on the one side the thing explodes. The formula becomes really horrible. It's nothing you want to work with on an everyday basis. And on the other side, it's totally well behaved, not much changed. And this is basically the miracle of the log open correspondence, that these two, this very ugly sum reduces to such a nice, I don't know if you would call that nice, probably a lot of you wouldn't call that, but comparably to the second row, it's much, much nicer. Okay, and this brings me to my conclusion, namely that log local open combines very, very different words together, and maybe these words can learn from one another. There's probably a lot to come in the future. Right. Thanks.